Hello and welcome to our Assignment 2 presentation on machine learning for data analysis. Today, we will provide an overview of the three modalities analyzed in this project: tabular, text, and image. A major theme of our work is the direct transition from our exploratory data analysis in Assignment 1 to the machine learning pipelines of Assignment 2. Throughout this presentation, our key objectives will be evaluated using metrics such as accuracy, macro, F1, latency, and model size. Let's begin with our first section, tabular ML, focusing on the ad-click dataset. For the tabular modality, we worked with the advertising dataset, 1000 rows, 9 raw columns, and a binary target, whether a user clicked an ad. The data is clean, perfectly balanced, 50, 0 missing values, 0 duplicates. I want to highlight how directly our Assignment 1 EDA shaped the ML decisions on the right. At topic, line, and city were near unique per row, so we dropped them. One hot encoding would have produced a memorization vector. Country had 237 levels, so we target encoded without a fold CV inside the pipeline to stay leakage safe. And because classes are perfectly balanced, we deliberately chose no class weights and no SMOD. Accuracy is a valid headline metric here. To serve both model families, we built 2 column transformer branches. The linear branch, used by logistic regression, applies a standard scaler because LR is scale sensitive. The tree branch, used by random forest and hist gradient boosting, skips the scaler entirely because tree splits are scale invariant. Both branches share the median imputer, the male pass-through, and the out-of-fold target encoder for country. The critical point: every learned statistic, means, medians, target encoding values, lives inside the pipeline. Nothing is fitted on the full dataset before splitting. That's what makes this leakage safe. With pre-processing locked in, we ran 5-fold stratified cross-validation on 3 model families. Logistic regression, random forest, and histogram gradient boosting, using identical folds so the comparison is fair. What you can see immediately from this chart is that all 3 models score above 4.95 across every metric. The dataset is easy. Random forest takes best CV ROCE AUC as 0.9911, so we promoted it to the tuning stage. But I want to be honest about what these numbers actually say. Random forest beats logistic regression by 0.028 in ROCE AUC, which is smaller than either model's standard deviation of about 0.104. So this is a statistical tie. A different random seed could easily reshuffle the ranking. In fact, AR leads on accuracy, 96.6% versus 95.8%. because AUC and accuracy reward different things. Accuracy rewards the 0.5 threshold decision. The overfit gaps are benign. Half gap of 0.08 is structural. Unpruned trees always memorize the training fold. HGB 0.003 is the largest, worth monitoring if deployed. Our decision was to promote random forest on the strength of best AUC and best PR AUC, but we acknowledge LR as a genuine runner-up, not a clear second. For tuning, we used randomized search CV with 40 configurations over the same 5 folds, optimizing ROCE AUC. The best score we found was 0.9 and fits Eve, 4/10,000ths above the default random forest. We chose random search over grid because at 40 iterations, a grid would waste budget on axis-aligned combinations. Random search covers the space uniformly and is strictly better in the dimensions that turn out not to matter, which, as the next slide shows, was most of them. AU span only 0.1006 from 0.9909 to 0.9915. The search has effectively converged. Further tuning offers diminishing returns. Notice also that hyperparameters barely matter here. Depth values of none, 6, 12, and 16 all appear in the top 5, alongside every possible max of features setting. The data signal dominates the model configuration. The winner's train AUC is essentially 1.0. Expected with max depth none, the model memorizes the training fold. The true test is the held out 200 rows, which is Act 3. Honest rate tuning gave us 0.404 over the default. Real but unimpressive. We refit the winning configuration on the full 800-row training set and evaluated on the untouched 200-row test set. All generalization gaps are within 3 percentage points. The log loss gap is expected, and unpruned RF outputs near 0 or 1 probabilities on training rows, so log loss explodes on the train side but stays reasonable on test. And here is the caveat I want to highlight. With only 200 test rows, percent confidence interval on test AUC is 0.972 to 1.1000. So when we quote 0.989, the honest reading is somewhere between 0.98 and 1.02. Point estimates at this sample size are noisy. At the default 0.5 threshold, 97 true negatives, 3 false positives, 3 false negatives, 97 true positives. The model has no class bias. The rho-fit curve hugs the top left corner, AUC 0.9989. The precision, recall, curve hugs the top right, Honda 93, both exceed 0.98, indicating near perfect ranking and near perfect precision at every recall level. AUC is expected on balanced data. 2 last mile tweaks. First, calibration. The uncalibrated Brer score was 0.0292. After isotonic calibration, it dropped to 0.0261, a 10.6% improvement. Meaningful, not spectacular. The reliability curve shows the raw forest is mildly underconfident and isotonic flattens the S shape. We adopted the calibrated version. Second, threshold tuning. Instead of defaulting 2.5, we searched for the threshold that maximizes F1 and got 0.73. At that operating point, accuracy, precision, recall, and F1 all sit at or 0.97. But I want to flag this explicitly. 0.73 is aggressive, it leans toward precision. That's the right call only if a false click prediction costs more than a missed conversion. Ultimately, that's a business cost matrix question, not a max F1 question. Limited or data limited, we ran a learning curve. Validation AUC rises from 0.983 at 64 rows to 0.992 at 557 rows, then flattens. Train AUC sits at 1.8 throughout classic RF memorization. The small train to validation gap at the largest size tells us we're not variance limited. More regularization won't help. And the validation plateau tells us the bottleneck is data richness, not model capacity. Doubling the data would yield at best marginal gains. Permutation importance tells a stark story. Daily internet usage and daily time spent on site together carry more than 95% of the predictive signal. Area, income, and age contribute marginally. Country, male, and the entire timestamp block, the features we spent the most engineering effort on, contribute essentially zero. Honest take, they could be dropped with no practical loss in AUC. The Shap beesworm on the right confirms what EDA hinted at. Low internet usage pushes the prediction toward click equals 1. Power users are ad blind, casual users click. We slice test performance by age quartile. Daily internet usage quartile, income, and gender. No slice breached our flag threshold of a 0.5 AUC drop, but 2 came close, the youngest age quartile at -0.41, and the mid-high DU quartile at -0.48. Those are the weakest corners of the feature space, worth monitoring in production. Caveat: each slice has only about 50 rows, so these gaps may be noise. To summarize, our final tabular model is an isotonic calibrated random forest, 587 trees, no depth limit. The headline is test raw CPU is 09A85, bootstrap 955%, CI 0972 to 1000. At the F1 optimal threshold, all 4-point metrics are at or above 0.97, but we're deliberately upfront about the limits. LR essentially tied RF and cross-validation. 3 of our engineered features added no measurable signal. With only 200 test rows, every point estimate has wide uncertainty, and the learning curve is flat. Further progress needs new features or more data, not more tuning. Next steps: interaction terms, A/B test against current rule-based targeting, and a monthly calibration read audit in production. That concludes the tabular modality. Over to the home for the text section. For the text modality, we worked with Stanford SQUID 1.1, a reading comprehension dataset with over 98,000 questions. Since SQUID is not a classification dataset by nature, we redefined the task as question type classification. Given a question, classify it into one of 8 types: what, who, when, where, how, which, why, or other. Every ML decision we made was directly motivated by what we found in assignment 1. For example, EDA showed that what questions dominate at 34% of the training set. So we used classy weight balance to prevent the model from just always predicting what. We also noticed why questions are extremely rare at under 2%. So we chose macro averaged F1 as our primary metric. This penalizes failure on minority classes. Finally, since questions are short at around 10 words on average, we used TF-IDF with bigrams to capture phrase patterns like how many or what year. Before feeding questions into any model, we applied a 6-step pre-processing pipeline. First, we take the raw question string, then we lowercase everything, remove all punctuation using a regex pattern. In step 4, we remove common stop words, but critically, we keep the question words like what, who, when, because these are the primary classification signal. Step 5 extracts the label by looking at the first word of the original question. Finally, step 6 branches into 3 parallel feature extraction paths. A concrete example, the question "when did the first Olympic Games take place?" becomes "when first Olympic Games take place" after pre-processing and gets the label "when." Looking at the label distribution, we have a serious class imbalance problem, a 31:3 times ratio between the majority class what with 3764 samples and the minority class Y with only 2 samples. The other category is the second largest but will turn out to be the hardest to classify, and I'll explain why shortly. Also worth noting, question length varies by category. Other questions are the longest at 11.6 words on average, while where questions are the shortest at 8.2 words. This is because other contains inverted questions where the question word appears in the middle of the sentence, not at the start. This slide shows what words appear most frequently in each category after stop word removal, and the patterns are very revealing. How questions are dominated by many appearing for 262 times. That means over half of all how questions are how many variants, where questions uniquely lead with a located, a very strong discriminative signal. But notice that what and other share many of the same top words: year, name, city, first. This overlap directly explains why our traditional model made 887 other. To what errors? The model sees these words and defaults to predicting what. We tested 3 feature extraction methods combined with 3 classifiers, giving us 9 traditional pipelines in total. TF IDF consistently outperformed bag of words and character hash embeddings across all 3 classifiers. The best traditional accuracy was 86.52% with TF IDF combined with random forest. Character hash embeddings performed worse. The 5-to-1 dimensional representation is simply not rich enough to distinguish question types that share vocabulary. Among classifiers, random forest wins on accuracy but takes 20 times longer to train than linear SVM for only a marginal gain. This trade-off will become important when we discuss deployment. Here is the full ranking of all 10 pipelines, including DistillBar, one with 99.9% accuracy, and the gap to the second place TF IDF plus random forest at 86.3% is enormous, over 13 percentage points. Among traditional models, all 3 TF IDF pipelines occupy ranks 2, 3, and 4, confirming TF IDF superiority. Notice also the inference time column. Linear SVM and logistic regression are essentially instantaneous at under 0.01 milliseconds per sample, while random forest takes 0.05 milliseconds. DistillBR takes 20 milliseconds, orders of magnitude slower. This slide quantifies the speed accuracy trade-off explicitly. Is 200,000 times slower than TF IDF plus linear SVM, 20 milliseconds versus less than 0.1001 milliseconds per sample. The model size difference is equally dramatic, 255 megabytes versus under 1 megabyte. Our production recommendation is therefore, use TF IDF plus linear SVM for real-time applications. It gives 85.3% accuracy at essentially zero latency with a tiny model footprint. Use DistillBar only for offline or batch processing where accuracy is the top priority and latency is acceptable. To put our results in context, always predicting what gives only 44.97% accuracy and F1 macro of just 7.75%. Our best traditional model beats this by 41 percentage points. DistillBar beats the baseline by 55 percentage points. Looking at the plus breakdown for TF IDF plus random forest, most categories perform very well. Who at 96.8, Y at 98.4, Where at 95. But the other category is a disaster at only 50.1% for one, with recall as low as 36.6%. This means the model correctly identifies fewer than 4 in 10 other type questions. This is the central weakness we need to explain. We fine-tuned DistillBRT based uncased on SQA for 3 epochs using Atom Optimizer at a learning rate of 2E5. Training took 5 hours on an Apple M series GPU via MPS acceleration. The result is 99.89% accuracy, and I want to be transparent about why. Question type classification based on the first word is actually lexically trivial for a pre-trained transformer. The first token, what, who, when is a near-perfect predictor of the label. The transformer's bidirectional attention understands this immediately. The real value here is not the accuracy number itself, but demonstrating that the full fine-tuning pipeline works correctly end-to-end, including tokenization, label mapping, and evaluation. Let's dig into where the traditional model fails. 72% of all errors, 87 out of 225, involve the other category. The root cause is a structural limitation of our label extraction method. We classify by first word, but other questions have the question word somewhere in the middle. 3 examples illustrate this clearly. Peyton Manning took how many different teams to the Super Bowl. The model sees how many in the sentence and predicts how, but the actual first word is Peyton, so it's other. What day was the Super Bowl played on? This starts with what, but gets predicted as other, because it's an unusual date. Type question the model associates with when, and how did Luther's tutors advise him to test what he learned? Overrides the leading how. The embedded what. This is not a model weakness, it's a labeling limitation. The label extraction rule of using the first word simply breaks down for these inverted constructions. These 3 slides show the confusion matrices for all 9 traditional pipelines, grouped by feature type. Looking at the TF-IDF group, as accuracy improves from logistic regression to random forest, the what column absorbs fewer other errors from 677 down to, well, still 887 for random forest. Interestingly, random forest concentrates errors differently. It pushes more other samples into the what column specifically because it becomes more confident in its predictions. In the Baowu group, performance is slightly weaker overall, with the other row even more scattered. The word embedding group is the weakest, showing 971 other samples predicted as what, with the logistic regression matrix 1 consistent insight across all 9 matrices, which has low precision because the model over predicts it for some other questions the word, which often appears in the middle of other type sentences. And here is the Digital Fusion matrix, a nearly perfect diagonal. Only 1 error in 10 5070 validation samples. The single failure is other predicted as which for the question that does TARDI stand for. It starts with the word that, not a canonical question word, and the model associates stand for with which type questions. Compare this with the TF-IDF plus random forest matrix where the other row had 225 errors. The still bar reduces this to 225 times improvement on the hardest category. This confirms that full sentence context understanding, not just first word heuristics, is what's needed to correctly classify inverted questions. Moving to the third modality, we analyze the Street View House Numbers, or SVHN dataset. We have nearly 100,000 images across 10 classes. However, our approach wasn't generic, it was directly dictated by our Assignment 1 EDA findings. Specifically, we addressed the low contrast through dynamic jittering. Most importantly, we accounted for the 3.03 times class imbalance, where digit 1 dominance and digit 9 is rare, by applying balance class weights to our loss functions. Finally, we decided to resize images from 32 by 32 to 224 by 224, allowing us to leverage the semantic power of pre-trained deep networks. In ACT-I, our goal was to establish a baseline. We wanted to prove that better features beat better algorithms. Instead of feeding raw pixels into a model, we used a frozen ResNet 18 as a feature extractor. This transformed every image into a 5112 dimensional embedding vector. We then tested 5 different classical classifiers, from simple naive Bayes to complex random forests, to see which could best interpret these high-dimensional deep features. Looking at the results saw a clear linear dominance. Logistic regression and linear SVM achieved nearly identical accuracies around 62.5%. The reasoning here is that deep features from ResNet are already highly structured, making them easy for linear hyperplanes to separate. However, from an engineering perspective, logistic regression was the clear winner, training 3.3 times faster than SVM while maintaining the same performance. To understand our 62% ceiling, we look at the diagnostics for logistic regression. On the left, the per-class F1 shows the model is stable, but on the right, the confusion matrix reveals the struggle. Even with deep features, the model is having a hard time distinguishing between structural shapes. Our reasoning for the ImageNet features are designed to recognize generic objects like cars or dogs, not the specific nuances of SVHN typography. We see massive confusion between digit 1 and digit 4 and 1 versus 7 simply because the frozen features overlap in vertical and angular strokes. This confirmed that while deep features are good, they need to be fine-tuned for this specific task. This led us to ACTE, the pipeline tournament. We didn't just want accuracy, we wanted to find the sweet spot of engineering. We tested 8 targeted pipelines, comparing ResNet and MobileNet backbones, different levels of PCA dimensionality reduction, and various classifiers. Our fastest training time dropped to just 128 seconds, while our best accuracy capped at 62.48%. Why these specific components? We included MobileNet V2 to test for edge deployment feasibility because it's much lighter than ResNet. We used PCA to combat the curse of dimensionality, testing if we could slash the feature space from 5012 down to 128 without losing the explained variance necessary to recognize digits. As you can see in the rankings, the known strategy, meaning using the full feature space, consistently took the top spots. ResNet 18 paired with logistic regression emerged as our top-ranked classical pipeline. The core insight here is the non-advantage. Preserving the full semantic space yielded the highest accuracy, proving that modern classical models can handle 512 dimensions without a problem. Furthermore, the continued dominance of logistic regression over random forest suggests that our extracted feature space is essentially linearly separable. This is our full 7 metric engineering profile. We tracked not just accuracy, but precision, recall training time, inference latency, and model size. This is a real-world evaluation beyond a simple leaderboard. Here is the trade-off reasoning, while known 1 on accuracy. PCA 128 was our efficiency triumph. It slashed training time to under 2 seconds with negligible accuracy loss. Additionally, MobileNet V2 proved to be the latency champion. If we were deploying this on a self-driving camera, MobileNet V2 would be our choice due to its superior inference speed. Even in our best tournament pipeline, we see the same diagnostic patterns we saw in ACTI. The F1 scores are balanced, but the confusion matrix is hitting a wall. This is our frozen performance ceiling. Mathematically, we've proven that classical ML cannot break the 63% barrier on frozen features. The vertical stroke overlap between 1s and 4s is a fundamental limit of the ImageNet backbone. To solve SVHN, we must move to ACT-ETER and unfreeze the network. ACT-EWARE, deep transfer learning. We moved from linear probing to full fine-tuning. We ran a 5-model tournament ranging from head-only models with 5,000 parameters to full fine-tuned models with 11 million parameters. This allowed the network to rewire its hierarchical features specifically for SVHN typography. Our setup was rigorous. We used a cosine annealing learning rate to ensure we didn't overshoot the minima and implemented early stopping to prevent overfitting. This was run on an M2 Mac using Metal performance shaders for GPU acceleration. These are the training curves for our winner, ResNet 18 full fine-tune. You can see the rapid convergence and the stability of the validation loss. The reasoning for this performance is twofold. First, the ImageNet initialization provided a massive head start, allowing accuracy to jump above 94% in the very first epoch. Second, by unfreezing all 11 million parameters, the model successfully learned to ignore the cluttered natural backgrounds of the VHN images, focusing purely on the digit geometry. Here is the final state of the art diagnostic. The confusion matrix is now nearly diagonal, with our accuracy reaching 96.32%. Our final macro F1 of 96.4% proves that we completely solved the class imbalance issue. The only remaining errors are structurally intuitive. The model occasionally confuses 3s for 9s or 7s for 1s. These are typographic ambiguities that even a human might struggle with, indicating our model has reached human-level performance on this dataset. To conclude the image modality and to wrap up our entire presentation, let's look back at this 3-act story. We moved from a fragile 47.1% baseline with raw pixels through an approximate 63% accuracy with frozen ResNet features to a final 96.32% success through deep transfer learning. This evolution of representation learning proves a core truth in modern AI. The quality of your data representation is just as important as the model itself. Thank you very much for your time and for following our project.